To whoever's watching this, my name is Maharshi, and I'm joined today by Jacob Lee.
Hey.
I'm joined by Eric Jean.
Hi.
I'm joined by Jiwon Lee.
Hello.
And today we will be presenting our RockSim project. And so I'll just get straight into the demo. This is the Windows demonstration. All right, and as you can see, these are our particles here. We have an environment scene. Not all of these things are working as right now, as this is the beta, but I can show you the simulation. As of right now, this is currently just using the CPU for computations, and I can also make collisions happen between the particles by just checking this off, and I can make it so that that also doesn't happen by unchecking this. I can show a grid. I can also enable downwards gravity, just like that. Disable dampening so that less energy is lost per collision, and increase the simulation speed. I can also just purely stop the simulation and terminate it, restarting it from the very beginning. Now then, this is the Windows implementation. By the way, just an FPS counter, object counter, and a memory count as well. We can go over to the Linux version as well. And so running this really quickly, you can also see approximately the same thing, but this is running HIP SDK over here. And so we have some actual GPU acceleration. Now, if the collisions doesn't work in this yet, because we haven't enabled that feature yet, but we can show grids and we can essentially do the same features over here, increasing dampening or decreasing it, et cetera, et cetera. And so this is the overall project as for now. We will be implementing some new features with like new simulations, such and such, but that is for Deliverable 3. Now then we will be moving on to explaining some of the design patterns that we have implemented. And so I believe Eric Jean will be taking it from here.
So we used the singleton pattern as our creational pattern in the OpenGL widget class as shown here, which is implemented by just maintaining a static instance pointer that just stores a single global object in memory. And its constructor is declared private, so like external code from other files can't create new instances of it. And instead, we just used a static get instance method, which returns the instance if it doesn't exist yet. And the copy constructor will also be explicitly deleted, so it is also impossible to duplicate the singleton. And this just makes it all so that all the code accesses like the same OpenGL object for rendering.
We will be moving on to the facade pattern. Now, G1, could you tell me which file to go on for your facade pattern?
Yep. So we use this in two places. So first, facade is on main window. And it hides the complexity of managing multiple UI panels, scene trees, and configuration dialogues behind the simple interface. The second facade is used in simulation facade, where this decouples our UI from the complex physics engine. So instead of the UI talking directly to dozens of simulation components, it uses clean methods like set gravity and toggle collisions. And so the benefits here, when we need to change our physics engine, we only update the simulation facade and the UI remains untouched. Okay.
All right.
And
perfect.
Mm-hmm. Yeah. So for the strategy pattern lets us switch between different physics algorithms at runtime based on the user's hardware. And we have three strategies: GPU acceleration using HIP and ROCm for high performance computing, CPU with collisions using the spatial grid detections, basic CPU physics for simpler simulations. And so the system automatically selects the best strategy. And if a powerful GPU is available, we use GPU acceleration. Otherwise, we fall back to optimize CPU algorithms. And the result, our application basically delivers the best possible performance on any hardware configuration. Mm-hmm. And the next is observer pattern. So for communication between components, we use the observer pattern through Qt signals and slots mechanism. And so how this works is when the particle simulation updates its statistics, it emits a stats updated signal, and the main window listens to this signal and updates the performance display automatically. And the advantage here is that this creates loose coupling. So components don't need direct references to each other, making the system more flexible and easier to test.
Okay, and now we will be moving on to the next part, which is the UI interactions. Jacob, could you guide me to whichever files you want to see?
Yeah, for sure. So we can go to the forms directory at the top with the main window.ui. So we have main window.ui is, I guess, our main window for where the users can interact with the program itself. Of course, we have many different buttons and parameters in here as well. You can see that we have the environment scene. So users are, I guess, will be able, I guess, for Deliverable 3 to kind of select which kind of objects are in play within the OpenGL widget. So they can select maybe item 1 could be like maybe 100 particles on it, and item 2 could be like 200 maybe squares in it, and they can kind of modify its parameters using the object inspector right below that. Currently, we only have size, so users can basically increase or decrease a set amount of size. Maybe like they can make it to 100, that's the maximum, or like 0.1 for the minimum. As well, we also have the configuration as well. It's basically just tuning the. You have to go to design. And it's basically you can enable the collisions, show grids, enable the HIP plugin if it supports HIP SDK. You can also turn down on its gravity as well, dampening and simulation speed as well. We have a play simulation and terminate simulation, and so basically users could pause and play a simulation to kind of get a sense of where the objects are. Terminate simulation just completely erases the OpenGL like instance of it and creates a new one. Also, we have the program menus at the very top. The file currently we only have if you can start up the simulation actually, Marshy, that'd be great. Yes, we have exit simulation as well as new simulation, and then if you click on new simulation, we would have a new tab basically where users can import existing, I guess, simulation JSON files, which we will be implementing for the Deliverable 3. So you can see it opens up a file explorer, and you can see it's JSON file only. So if you X that as well. And then our other one as we have is the help menu, which just redirects us to the GitHub page for information. So yeah.
Okay, perfect. Sounds good. So I will be talking a little bit more about the UI interactions plus backend and domain logic. So if we were to move over to the main window.cpp, we have some signals and slots over here, as you can see, connecting between the UI and the actual domain logic / backend over here. And so I'll talk a little bit more about the backend. Currently, we have two key backends. And right now, we have the CPU backend and the GPU backend. We can accommodate for all people by realizing that, hey, not everybody is able to support HIP SDK with their various GPUs, and some people just don't have the knowledge for it. And so if they're able to run the application, they can still run it with the CPU. And so there is obviously a lot of code to go over, but this just consists of some getters and setters and random things. So over here, we have our simulation toggling, and then more getters and setters for collision detection, gravity, and dampening. Some testing features for toggling grid display. The grid is specifically for collision detection mainly. And then we just have some particle features as to how to describe them and such, how to keep track of our FPS, and this will only be rendered if HIP is actually enabled. This is something that we have in our CMake file. In our CMake file, we detect if HIP is actually available or not. There's a lot of detail to go into, but this is just the overall for the CPU side. And then for the GPU side, we have a specific, we make our own specific kernel, which it's not actually part of the class, rather it's actually called by the class. GPU kernels cannot actually be part of an object-oriented class directly. And so rather we are just calling it. If I was to show you, for example, yes, as you can see, we are allocating space for it over here, and then we are launching it on a specific stream as well. And then if we were to look at it overall, this is the average particle structure. It has a mass, radius, its color, its velocity, and position. its position, initial velocities, and color and such are determined randomly. We have our spatial grid for collision detection. Note that this isn't enabled for the GPU version just yet, just for the CPU version. Then we have our constructor and destructor classes, updating particles, checking if HIP is available or not, and just this is to make sure if RAM is used or not. There's a lot of details, but obviously can't go over all of it right now. And so this is overall our project. Thank you so much for listening.